So we're going to talk about the elastic deformation of an axial member. We've already talked about this a couple of times already, but we're going to start looking at more and more complex loading scenarios for an axial member. And so just to refresh your memory what an axial member is, it's a member that's loaded with a force that's parallel to the longitudinal axis of the member and acts right through the centroid of each cross section of the member. And the advantage of that, or the simplification of that, is that when we make a cross-section cut on an axial member, we only have an internal normal force. So it limits the amount of internal resultants that we have to consider. And so this in chapter 4 of your Hibbler textbook, we start out relatively easy. We'll start looking at different types of internal resultants like torque, shear, and bending moment later on. But now in chapter 4, we're just focused on axial members. But what we've talked about so far is a relatively simplified look at axial members, and we're going to start looking at more and more complex loading and geometry for those members. So the first thing that we want to try to calculate is for elastic behavior limited to the linear elastic range of a material. Let's try to calculate how much a column, an axial member, deforms, how much change in length we get in an axial member. And so I have a diagram of a generic axial member provided over here on the left-hand side. I've provided a support on the left with some sort of reaction, horizontal reaction. The axial member has a non-constant cross-sectional area. We have two different externally applied loads. So we could have potentially a distributed axial load. So if this was oriented vertically, that could be due to, let's say, self-weight. Here that is oriented horizontally, it could be due to acceleration. It could be due to perhaps a wind, drag, something like that. And we also have a point force axial load at the end of the member as well too. So the idea is that this should apply to any type of axial member because the internal normal force is going to vary and the cross-sectional area is going to vary, which could cover any possible combination of loads and geometry. So our goal here is we want to figure out, subjected to these external loads, how much is this member going to change its length? We're trying to calculate if I were to draw the deflected shape of this member, because it's all in tension, I'm going to assume that it gets longer. And so this green dashed line is representing the deformed shape of the member. We have our original length, capital L, but what I'm interested in is the change in length. We'll use lowercase Greek delta for that. So in our simplified analysis before, we were able to calculate delta relatively easily. But in those previous analyses, we were assuming that the strain was constant along the length of the member, and the strain is not going to be constant here necessarily. There will be some cases where we can generically simplify the equation to cover those cases, but in this case, because the cross-sectional area varies and because the internal normal force is going to vary, as we see when we make a section cut, the strain will not be constant, and so we can't just multiply the average strain times the length. We have to do a little bit of calculus, as you'll see. So here, our generic diagram, we need to start figuring out, well, how are we going to calculate delta? How are we going to calculate the change in length? And one important thing that we're going to need to figure out would be, for example, the strain at any given point. And if you remember from Hooke's law that we learned about in chapter 3, Hooke's law says that the normal stress in a material in the linear elastic range is equal to the modulus of elasticity, capital E, times the normal strain. And so in this case, if we're trying to calculate the normal strain, we need to figure out the normal stress first. And so the normal stress, we can remember, relatively straightforward, is equal to the internal normal force divided by the cross-sectional area. And so here, just to go through the statics, if I want to figure out the internal normal force anywhere across the length of this member, I just need to make a section cut. So I'm going to make an arbitrary section cut right here. And actually I'm going to make two section cuts so we can take a slice out of this column. And so the distance of that we will call dx. I'll take a differential slice out of this member. I will take that section cut at an arbitrary distance, which I'll call x, from the left side of this column. So if I make that section cut, again here we're looking at external forces and support reactions. What I care about here are internal normal forces, not external normal forces. And so to get an internal normal force, I need to make a section cut and figure it out that way. Here, if I were to draw the resulting free body diagram from that section cut, I would get a small slice that has a distance dx. I'm going to have an internal normal force on either side. We can calculate that just by making a section cut. I'm just going to leave it as a variable here, and I'm going to call it capital N for the internal normal force. So we will have a small distributed axial force acting on this section cut as well too, but it's going to be so small I'm basically just going to ignore it at this point, and I'm going to say that it's essentially equal to 0 because this cut is so small. And so I'm going to say that this is just subject to a uniform normal force N on either side to keep it in equilibrium. We're just going to ignore the distributed load right here. Okay, so for this small section, this subject to a uniform normal force is also going to deform. And the amount of deformation that this is going to undergo for this small distance dx, I'm going to call the amount that this single section is going to elongate, I'm going to call that d delta, which is the differential contribution to the overall deformation, but just due to this small little slice, this small little section cut right here. All right, so a couple of things that we need to keep in mind is that if we're using this free body diagram here to calculate the internal normal force, the cross-sectional area in order to figure out the normal stress, we need to realize that along this column, anywhere that I make a section cut, both the area and the normal force could vary. Before we've dealt with situations where the normal force is constant, but here I have a distributed axial load that will affect the internal normal force at any given location. So this, in reality, is a function of x. The internal normal force will vary depending on where I am along the column. Likewise, the area, and we'll assume that the area is the same on either side, the area is also going to be a function of x. As you can see here, it starts out very shallow at the support on the left-hand side. It becomes much deeper on the right-hand side. So the area is also a function of the location of the section cut. And so I will rewrite the normal stress equation as equal to n of x over a of x. There could be an example, a specific example where this is constant, in which case these would go, one or the other or both would go to a constant value, but we want to capture any possible combination, any possible stress distribution. Okay, so that's the stress, that's the left-hand side of my equation. Here, if I wanted to find the strain, let's just do it for this small free body diagram here. And we know that the definition of strain is that it's equal to the change in length divided by the original length. So here, my change in length for this small section cut is d delta. and my original length is dx. So now if I take both of these definitions, I have the definition of my normal stress, I have the definition of my normal strain. I can take those and I can plug them in to this equation over here. And if I do that, I will get the equation n of x over a of x is equal to the modulus of elasticity times the normal strain, which we calculated as d delta divided by dx. What we're trying to do is not actually calculate d delta, we're trying to calculate delta by itself, the entire change in length of the whole column, not the change in length of a single element. And so simply all that we need to do is integrate and add up together all of the changes in length of these differential elements across the entire length of the beam. So if I'm trying to do that, I'll need to integrate d delta. I'm going to rewrite this to get d delta on a side by itself, and I will say that d delta equals n of x dx over a of x times e. But again, it's still in the form where it's the length, the change in length of this small differential element. If I want to integrate that over the entire length of the column, that's no problem. It's just some basic integration rule calculus. So if I integrate both sides over the entire length of that column, which is from 0 to L, on the left-hand side I will get delta. On the right-hand side I will get, this will stay as it is in this integral form. I will get the integral over the entire length of the column of n of x dx over a of x times e. So the overall change in length of this column is equal to the integral from 0 to L of the internal normal force as a function of x dx divided by the cross-sectional area as a function of x times the modulus of elasticity. So this is a fundamental equation of general applicability that we will use all the time in chapter 4. And you'll find that in your Hibbler textbook in like chapter 5 and even later on, this same kind of equation or a similar format is used for different types of loadings as well too. And so it's good to kind of get familiar with the way that it's formatted. And some things that I point out is we're going to find that when we're calculating the change in geometry of a member subject to a specific type of load, we often have similar types of components to our equation. So almost always, length is going to be an important part of that equation. For example, here, the longer that the column gets for the same amount of normal force, area, modulus of elasticity, we'll get more deformation. We've seen that before. We've talked about that in class. Likewise, we have a loading parameter. Here, the loading parameter is the internal normal force. And the larger that is, the more deformation we get, and that makes sense. The cross-sectional area, or some sort of geometric cross-sectional property, is also inherent in almost all of these deformation equations. Here, if the area is large, it'll decrease the amount of deflection, which also makes sense. And finally, we have the modulus of elasticity. And the modulus of elasticity, the larger it is, the less deflection we get because it's in the denominator. And that makes sense as well too. And so this general form equation, which we'll be using all the time, we don't always need to use it in the integral form. If we have the normal force varying across the length, then we might need to. Or if we have the cross-sectional area varying across the length, then we might need to. But we can simplify this down for other purposes, other situations that don't require the calculus format. And so, for example, we've already looked at, let's say, a tension test specimen. And if I took this tension test specimen and I applied let's say some load P, top and bottom, and I was trying to calculate what the change in length was from an original length of L. If I make a section cut here and make my free body diagram, I'm going to find, here's my section cut, my external load is P, my internal normal force is also going to be equal to P. I kind of skipped some steps, but I just made a section cut. I drew my internal normal force in the assumed positive direction, and then I used equilibrium to solve, and I know that N is equal to positive P, a very simple kind of free body diagram. All right, so if we calculate our internal normal force, we notice here that it's a constant value. So my internal normal force in this specific example is not a function of x. It's just a constant value. And if you remember from integral calculus, any constant values inside of the integral we can take out. So n, in this case, I could just take out of the integral if I wanted to. Likewise here, if we have a tension test specimen like we looked at in chapter 3, the cross-sectional area is going to be constant the entire height. Oftentimes with like a metal test specimen for a tension test, it's often a ½ inch diameter and constant the entire way, at least the zone that we are considering. So here the area is also going to be constant. So we'll have a constant cross-sectional area, I'll just call it A. So in this simple situation where the normal force is uniform and where the cross-sectional area is uniform across the entire length of the column, N and A are constant. E, the modulus of elasticity, we aren't going to talk about any situations where the material properties are different at the top than they are at the bottom, so we're going to assume that E is also a constant. So in this specific situation, I can simplify this down, and I can say that delta is equal to, if I take N out of the integral, and if I take A and E out of the integral, all that I'm left with is the integral from 0 to L of dx. And here, integral of 1 of just dx is going to be equal to x. If I evaluate that at L and at 0, I get a value of L. So this simplifies down to NL over AE. Another very handy equation, and we don't need to use calculus or integration to figure out the change in length. But again, remember the caveats. That means that only here, N is a constant value, and A is also a constant value. That's when this applies. If both are not constant over the length of the column, then you need to use the integral form of that equation. So there could be other situations where the simplification would only be to take N out of the integral because it's constant, or only A out. And so you could also have a situation where delta equals N times, we'll take E out as well too, times the integral from 0 to L of dx over A of x. So this applies only if N is a constant. And the corollary would be that we take A out of the equation, so we get 1 over A times E times the integral over the length of N of x dx. These are a little bit less rare, but any one of these could apply. Fundamentally, and let me put this down, that A has to be constant in this example. This is the general equation. It always works. This is a commonly used simplification if the normal force is constant, the cross-sectional area is constant, and then these would just be specific if one or the other is a constant. And we will use these constantly. So we'll do a couple examples where we'll use the general form equation. We'll also have some other uses for this equation where even though technically for a member the normal force or the cross-sectional area is not constant, we can sometimes break up a column into multiple different sections and treat them as individual columns by themselves. So the example of that would be a column that looks like this, where I have two different sections. Let's say this is a circular column, a large diameter and a small diameter, and let's say that it's subject to a point load right here and a point load right here. We'll say P1 and P2. It'll have some reaction as well. And for this first section, I'll say that it has an area A1, and here it has an area A2. So in this situation, my internal normal force in this first section will be different than my internal normal force over here. All right, you make a section cut, you draw your internal normal force in the assumed direction, you use statics, equilibrium to calculate the internal normal force. It will be different here than it is here. The cross-sectional area is different as well too. And so if I want to calculate the overall change in length of this entire assembly, really all that I have to do is superimpose the results of the change in length of this first section plus the change in length of the second section. It really breaks down to there'll be some portion of the overall change in length that's due to the first section, and the other portion, the change in length, will be due to the second section. So here, really, the point is that in between here, I'll call this point B, C, and D, between points B and C, it acts like a single column with a constant normal force, a constant cross-sectional area. So here for delta 1, it'll be NL over AE for section 1. Over here, my delta for section 2 will be equal to NL over AE for section 2. And I just add the two results together to get the overall deflection of point D to the right. And so to modify this simplified equation here, I'm going to put a sigma in front of NL over AE. Because if you can break down a column into individual components where N and A are constant, then you can break it down and just do NL over AE for each of them. It makes life quite a bit easier. So we'll use this a fair amount. The tricky part with a problem like this is making sure that you get the correct internal normal force. Sometimes people would be enticed to use P1 and P2 for the internal normal forces. And that would actually work for this second section, but P1 is not going to be equal to the internal normal force in the second section. Again, remember, this is an external force. This is an external force. What we care about here are internal normal forces, and they're not the same thing. The external forces cause the internal normal forces, but you can't just pull the value of the external forces and treat them as internal. Like I said, it works for the second section, but it won't work here. And we have a video already posted that goes through developing a normal force diagram that goes through that process, but it's all statics, making a section cut, drawing your internal normal force, then calculating the magnitude.